You walk across a carpet in dry winter air, reach for a metal door handle, and feel a sudden, sharp crackle of static. That momentary spark is the physical discharge of electric charges that have accumulated on your body. The earliest recorded observation of this unseen force dates back to Greece, around 600 BC, with the philosopher Thales of Miletus. He noted that rubbing fossilized tree resin, amber, with a piece of wool or silk allowed the amber to attract light objects like bits of straw. The ancient Greek word for amber is electron, which provides the modern term electricity. Through centuries of careful experimentation, scientists established that these charges possess polarity. There are exactly two distinct kinds of electric charge, which we conventionally designate as positive and negative. By the 18th century, instruments like the gold leaf electroscope were designed to physically detect the presence of these charges. When a charged object touches the top metal knob, charge flows down the vertical rod to two thin gold leaves. Because like charges repel, the leaves push apart. The degree of their divergence serves as a direct physical indicator of the amount of charge. While the electroscope proved that electrical charges existed and exerted force, the vast invisible volume of space surrounding those charges remained entirely unmapped. To characterize the electrical environment around a system of charges, physicists use the concept of an electric field. At every single coordinate in space, this field dictates the exact force a hypothetical unit-positive test charge would experience if placed there. Calculating discrete Coulomb force vectors for every point in a three-dimensional volume results in an overwhelming array of numbers. It is highly difficult to visualize. In the 19th century, Michael Faraday sought a way to bypass the purely mathematical abstractions of his contemporaries. He invented an intuitive, non-mathematical method to map this environment visually, drawing what he termed lines of force. Today, we refer to them as electric field lines. They translate abstract vector equations into a highly legible geographic map of unseen forces. This diagram shows a single positive point charge placed at the origin, surrounded by discrete vector arrows. Vector arrow length is proportional to field magnitude. Because the field decreases inversely as the square of the distance, arrows get shorter moving away. Connect the separate arrows and the discrete shapes smoothly merge. The resulting continuous curve is defined as an electric field line. This establishes the first primary geometric rule. An electric field line is a space curve drawn so that the tangent to it at any given point perfectly matches the direction of the net field at that point. A single smooth line acts as a strict set of instructions, dictating exactly the direction a positive test charge is pushed along that path. By converting discrete vectors into continuous lines that stretch infinitely, we lose the length of the individual arrows. How do we read the field's strength? This visual model illustrates the second rule. The magnitude of the field is represented by the relative density of the field lines. Density means the number of lines crossing a unit cross-sectional area perpendicular to those lines. Look closely at area element R near the charge. A high concentration of field lines pierces this surface. In three-dimensional space, the total spherical area enclosing the charge increases as the square of the distance. Now observe area element S. It has the exact same dimensions as R, but is further away. Significantly fewer lines pierce this surface. Because the total number of lines originating from the charge remains constant while the surrounding space expands, the number of lines crossing our specific unit area drops off by a factor of 1 over r squared. Field lines physically crowd together where the electric field is strong and spread apart where it is weak, creating a visible measure of magnitude. Single point charges establish the baseline rules, but real-world physics involves multiple interacting charges. Here is an electric dipole, a pair of equal and opposite charges separated by a distance. Notice the strict directional flow. Field lines always originate at positive charges and terminate at negative charges. These unbroken, arching loops map the physical reality of mutual attraction. If we replace the negative charge with a second positive charge, the system updates immediately. The lines snap apart and push outward. They crowd tightly together in the space between the charges, indicating a strong electric field, yet fiercely veer away to avoid connection. The macroscopic geometry of the lines visually calculates the complex superposition of multiple repulsive forces instantly. The geometry governing these diagrams rely on strict physical imperatives. Take this scenario, where two distinct electric field lines converge and form an X by crossing over each other. Topologically, this is forbidden. Two electric field lines can never cross. If we zoom in on that precise point of intersection and apply the tangent rule, the problem becomes obvious. Two distinct conflicting tangent vectors emerge from a single coordinate. This creates a physical impossibility. A test charge placed precisely at that intersection would be instructed to move in two different directions simultaneously. At any single point in the universe, the net electric field can only possess one unique direction. There is a final restriction. Electrostatic field lines do not form closed loops. This behavior is a direct mathematical consequence of the conservative nature of the electric field. Because magnetic fields do form closed loops, Faraday's original term, lines of force, can be somewhat misleading. Modern physics uses the more precise term, field lines, to maintain this distinction. Within any charge-free region of space, these field lines must remain continuous curves without any sudden breaks or gaps. The tangent provides the unique direction of the force, and the relative density of the lines provides the magnitude. Electric field diagrams are rigorous geometric maps that reveal how fundamental forces are distributed through the space around us.